Have you ever stopped to think about how we communicate digitally now? I mean, the internet's just there, right?
hmm
But what if I told you there was this whole really fascinating chapter way before the modern web? People sending messages, sharing files, building networks, all using radio
Oh,
waves.
absolutely. Before the internet really took over everything, there was this really powerful mode in amateur radio called packet radio. And it genuinely changed the game for how hams talked digitally.
And that's exactly what we're diving into today. This is our deep dive on packet radio. We're going to explore how this tech brought digital comms, messaging, networking, all that stuff to amateur radio operators. Think of it as your shortcut to getting really up to speed on this.
Yeah, and our main source here is this really comprehensive multi-part guide written by an expert, someone who is really in the thick of it. It gives us the history, the tech details, and, practical advice on how people actually used it.
Then we'll get into some surprising bits too, like how they managed to get almost error-free communication over noisy radio
Right.
waves, or how this global info network worked without any commercial internet. It's pretty cool stuff. Let's start unpacking it.
Okay, so setting the stage, we got to go back to the early days. Digital communication for hams.
Hmm.
It was pretty rudimentary at first.
Right.
And, interestingly, Canada was actually ahead of the curve here.
Really?
Yeah,
Canada?
Canadian hams got the green light to transmit digital packet radio about a year and a half before the U.S. did.
Wow, that's a decent head start.
It was. And a key figure was Doug Lockhart, VE7 APU, up in Vancouver. He developed the very first terminal node controller, the TNC. He called it the VADCG board.
The TNC, that sounds important.
Oh, it was the foundational piece of hardware. Basically the magic box that turned radio signals into digital data streams and back again. He also started the Vancouver Amateur Digital Communications Group, VADCG.
Okay, so Canada's pioneering it. When did the U.S. jump in?
Well, the FCC, the Federal Communications Commission, gave the okay for ASCII transmission, that's, standard text for hams, in March of 1980. Then, in December of that same year, things really kick off in the U.S. Hank Magniski, KA6M, down the San Francisco Bay Area, he not only developed his own TNC, but also put a digital repeater on the 2-meter band.
A repeater, so like extending the range digitally.
Exactly. And that effort led to the Pacific Packet Radio Society, or PPRS.
And it wasn't just a West Coast thing, I assume?
Not at all. You had AMRAD, the Amateur Radio Research and Development Corporation over in Washington, D.C. They became the East Coast hub. And then TAPR, the Tucson Amateur Packet Radio Corporation, founded in '81 down in Arizona.
TAPR, that name comes up a lot, doesn't it?
It does. They were hugely influential. And crucially, these groups, PPRS, AMRAD, TPROF, and S, they didn't just work in silos, they collaborated.
Oh, smart.
Yeah, and that collaboration led to AX.25, Amateur X.25. It was basically a modified version of a commercial data protocol, X.25.
So standardization, making sure everyone's gear could talk to everyone else's.
Precisely. That was key. And then the big moment for, the average ham operator came in November '83.
What happened then?
TAPR released the first TNC kit, the TAPR TNC1.
A kit, so people could build their own.
Exactly. That really opened the floodgates.
Yeah.
1984 saw tons of experimentation. People started writing software for packet bulletin board systems, BBSs, and packet just exploded across the U.S. and Canada. Thousands of hams caught the packet bug, as they called it.
So what does this all mean, really? It sounds like more than just a new gadget.
Oh, definitely. This wasn't just some technical curiosity. It was a major leap. It gave hams capabilities they just didn't have before. Digital messaging, file sharing, networking. It changed how they could interact, share info, even how they could help in emergencies.
Okay, that's a great picture of how it started. But for someone who wasn't around then, you might be asking, okay, what is packet radio fundamentally, and how did it actually work?
So, at its core, packet radio is a specific mode of amateur radio. And it had a huge range of uses. You could do local keyboard-to-keyboard chats, QSOs.
The typing back and forth.
Yeah. Or you could do long-distance contacts, DXing. It was great for electronic mail, sending messages reliably, supporting emergency communications. And honestly, it was just a fantastic playground for digital tinkering.
I can see the appeal. You mentioned QRM, the noise on lower bands. This must have seemed like a clean alternative.
It was a new challenge for folks tired of static, An alternative for FM operators, too. And way faster for message handling than older modes like RTTY radio teletype.
Which was pretty slow, right?
Painfully slow sometimes, yeah. So packets served everyone, the chatty types, The serious message handlers for public service, the experimenters, the casual users.
And the heart of it all was that TNC, the little black box.
That's right, the terminal node controller. You wired it between your computer and your radio.
So this box is doing the translation work, bridging the computer and the radio.
Exactly that. It had software inside to manage the transmissions, incoming and outgoing. And critically, it had a modem.
A modem,
Oh.
like for a phone line. Similar concept. But instead of phone lines, it converted the computer's digital data into AFSK tones audio frequency shift keying. Basically, different audio pitches representing ones and zeros.
Ah, okay, so tones the radio could actually transmit.
Precisely. And on the receiving end, it did the reverse, turn those incoming tones back into digital data for the computer. So yeah, very much like a telephone modem in function, just using radio waves instead of phone lines.
Got it. Okay, now the packet part. And this error-free communication. That sounds almost impossible over radio with all the fading and noise. How to manage that?
Yeah, that's really the secret sauce. The name packet comes from how the TNC bundles up the data and sends it in bursts or packets.
Little digital envelope.
Kinda, yeah. And each packet wasn't just raw data. It contained the sender's call sign, the recipient's call sign or address, the intended route if needed, the actual data itself, and this is the key part, error checking information.
Okay, so quality control built right in. Exactly. When a TNC received a packet, it ran that error check. If the check passed, great. The data was accepted. If it failed, maybe due to noise or interference, the receiving TNC just discarded it and didn't acknowledge it.
And the sending TNC.
It would wait a bit for that acknowledgement. If it didn't get one, it assumed the packet was lost or corrupted and would automatically resend it.
Until it got through correctly.
Right. This automatic repeat request system meant the communication was, well, as error-free as your typing allowed. It was incredibly robust for radio conditions.
That is really clever. And these packets, how much data could they hold?
Up to 256 characters, typically. And they could be sent pretty quickly, in just a couple of seconds.
Which sounds efficient.
It was. And because they were short bursts, there was usually plenty of dead air time between packets on a frequency. This meant several different conversations could happen on the same channel, sort of interleaved, without stepping on each other too much.
That does sound like a lot going on under the hood, though. You said it was easy to use.
Relatively speaking, yes, because the TNC, or the special packet software if you use that, automated all that complex stuff, the packetizing, the error checking, the resending. It handled the tricky bits. So the user can mostly just focus on typing their message.
Okay, so you've got your TNC, your little black box. How did you actually get connected and start talking to someone? What were those first steps?
All right. The basic setup was your transceiver, your radio computer, and the TNC.
Or that cheaper option you mentioned.
Right. Or a simpler special packet modem plus dedicated software. That could save you some money, maybe around $50 versus over $100 for a full TNC back then.
And the radio? Any specific type?
Well, the recommendation was usually to start on 2 meters, VHF. That's where most of the action was, especially locally. Though people definitely used 220 megahertz, 440 megahertz, even HF bands later on.
And hooking it all up. Cables?
Yeah, TNCs usually came with a generic radio cable, but you often had to solder on the specific connector's mic plug, speaker plug for your particular radio model. That could trip people up.
Okay. And computer to TNC?
That connection, usually a standard RS-232 serial cable, you typically had to provide yourself. Software-wise, if you had a TNC, pretty much any generic terminal program worked things like Procom or even the basic Windows terminal.
And if you use the modem instead?
Then you needed specific packet software designed for that modem, like Baycom was a popular one.
Got the gear, got the cables, got the software running. What next? Settings.
Settings were critical. You had 2 main data speeds, or baud rates, to worry about. One was between your computer and the TNC they had to match.
Okay.
The other was the actual speed the packets went over the air. Getting those right, along with other data parameters like 8 data bits, no parity, 1 stop bit, usually written 8 and 1, was crucial. Reading the manual is definitely not optional.
Right. And then understanding where your typing was actually going. You mentioned different modes.
Yes, absolutely vital. You needed to know which level you were communicating at. There were basically 3. 1, just interacting with your computer's terminal software. 2, talking directly to the TNC itself. This is called command mode. You'd see a CMD prompt.
They made it instructions.
Exactly. And 3, actually sending your data out over the radio to another station. That was converse mode. If you type something, thinking you were in converse mode, but you were actually in command mode.
It just goes to the TNC, not over the air.
Exactly. Your message goes nowhere useful. So knowing CMD versus talking to someone else was fundamental.
Makes sense. So walk me through setting up the TNC from command mode, power it on.
You turn it on, your terminal program should show some kind of greeting message from the TNC, if it's just garbage characters.
Baud rate mismatch.
Probably baud rate or those 8N1 parameters.
Yeah.
Assuming that's okay, you hit Control-C on your keyboard. That usually forces the TNC into command mode, showing the CMD prompt.
Okay, CMD prompt. First thing, tell it who I am.
Yep. MY call, followed by your call sign. So MY call, WB9LOZ. That's stored your identity. You might also type echo on N so you could see what you were typing.
Good idea.
And then, really important for seeing what's happening, monitor on. That lets you see packets being transmitted by other stations on the frequency. And MRPT on N specifically shows packets being repeated by digipeaters.
Okay, set up, call sign in, monitoring on, ready for that first contact, first QSO.
Right. Turn on the radio, volume maybe a third of the way up. Adjust the squelch knob just until the background hiss stops.
Standard radio practice.
Yep. Then tune to a known packet frequency. On 2 meters, that was often odd-numbered frequencies between 144.91 and 145.09 megahertz, or up between 145.61 and 145.79 megahertz. Set the radio for simplex direct communication.
And then you just watch the screen.
Pretty much. You're in monitor mode, so you'll start seeing packets fly by if there's activity.
What would that look like?
You'd see something like WB9LOZ, W6PW3. Meeting tonight at 7 p.m. shows who sent it, who it's addressed to, and the message.
Simple enough. Now, you mentioned an asterisk sometimes appearing, like W6PW1. What was that about?
Ah, good catch. The asterisk meant you received that packet via the station listed, W6PW1, acting as a digipeater. So the packet originated from WB9LOZ, but it was repeated by W6PW1 to reach you.
Okay, so it's showing the path, and the -1 or -3 part.
Those are SSIDs, secondary station IDs, allowed a single ham call sign to have up to 16 distinct digital identities on the air. So W6PW might have W6PW1 as a digipeater, W6PW2 as a BBS, W6PW3 as their personal station, and so on.
Handy. All right, so I see WB9LOZ is on. How do I connect?
Back in command mode, CMD prompt, you type C for connect, followed by their call sign, CWB9LOZ. If you knew you needed that digipeater, you'd add V for via. CWB9LOZ VW6PW9 miss one.
And if it works?
You'd see a message like connected to WB9LOZ, and crucially, your TNC automatically switches to converse mode.
Ah, so now whatever I type goes over the air.
Exactly. Type your message, hit enter, and out it goes. When you're done chatting, hit Control-C, or maybe ESC depending on the TNC software, to get back to the CMD prompt, then type D to disconnect.
And sometimes nobody answers.
Yeah, be patient. You might have connected to an unattended station or maybe a network node which wasn't meant for direct conversation.
Nodes. Okay, that brings us beyond just local chats or simple digipeaters.
Right.
Mastering the node network. What was the big difference there? Why nodes over digipeaters?
This is a really, really important distinction. It's all about efficiency and reliability, especially over longer distances. Remember how with digipeaters, your packet had to reach the final destination before an acknowledgement, ACK, came all the way back to you.
Right. Each hop adds delay and chance of failure.
Exactly. More hops meant more potential collisions, more interference, more retries needed. Performance dropped off fast. Dr. Tom Clark, W3IWI, did the math. Each hop could lose anywhere from 5% to 50% of packets, depending on traffic, and the ACKs had to make the same journey back. It wasn't great.
So how did nodes fix this?
Nodes, things like Netrum, the Net, G8BPQ switches, KA nodes work differently. Instead of end-to-end acknowledgement, they did node-to-node acknowledgement, meaning when your TNC sent a packet to the first node in the path, that node acknowledged it directly back to you once it received it correctly.
Ah, much faster feedback.
Much faster. Then that node took responsibility for forwarding it to the next node, which acknowledged it back to the first node, and so on down the line.
Like a reliable bucket brigade.
Perfect analogy. It dramatically cut down on retries because errors were caught and corrected hop by hop. This made long-distance communication, even with fairly low-power radios, much more reliable and expanded the range significantly. Nodes are often set up in high locations too, and used easy-to-remember aliases, like maybe Berkeley instead of WB9LOs2.
Okay, so how did you actually use this node network?
First step was connecting to your local node, just like connecting to a station. C Berkeley or C WB9LOs-2. Your TNC then went into converse mode, but you were talking to the node.
Right, not directly over the air anymore.
Correct. Now, from the nodes prompt, if you wanted to connect to another ham, say K9AT, you just type C K9AT. The node handled figuring out the best path to reach K9AT through the network.
Okay. And what if K9AT was far away, reachable only via other nodes?
Same process. While connected to your local node, Berkeley, you type C followed by the distant node's alias or call sign, maybe C Gold D or CW6ABC3. You didn't need to know the path yourself.
The network figured it out, like early internet routing.
Very much like that. The node network maintained routing tables and found the best path automatically. No more needing to manually string together VW6PW1V N6XYZ-4V like with digipeaters.
That's a huge improvement. Now, you mentioned SSIDs changing.
Yeah.
How did that work with nodes?
Yeah. To avoid confusion, if a station could hear your packets both directly and relayed via the node would often change your outgoing SSID. A common way was using the formula 15 minus N, where N was your original SSID number. So if you connected as WB9LOZ0, packets forwarded by the node might go out as WB9LOZ15.
Clever. Prevents duplicate packets causing issues.
And disconnecting from the node. Go back to command mode Control-C, usually then type D for disconnect. Some nodes also had a BYE or B command. This would disconnect you from the distant station and the entire node path back to your local node automatically.
These nodes sound pretty smart. What other features did they have? Could you see the network?
Oh yeah, most nodes had commands like nodes or just N that would list all the other nodes that this node knew how to reach, showing their aliases and call signs. Gave you a map of sorts.
Could you check the quality of a path?
Yes. You could often type N followed by a distant node's alias, like NGOLD. It would give you a route report, maybe showing up to 3 possible paths. And crucially, it showed the quality of each path.
Quality, like signal strength.
Sort of a measure of reliability. 255 usually meant a direct wired link. 192 was typically the best over-the-air single-hop connection. Lower numbers, especially below 80, meant a difficult path. It also showed an obsolescence count, how recently that path information was updated.
So you knew before trying to connect if a path was likely to work well. Saves time.
Exactly. Save tons of frustration trying to connect over bad paths. You could also use routes or R to see just the direct connections from the current node to its immediate neighbors, again with quality and age info. An exclamation mark often meant an unreliable, manually entered route.
Could you see who else was using the node?
Yep, users or U command. Showed call signs connected to the node and how they were connected, maybe coming in from another node, UPL Inc., connected directly.
Yeah.
Downlink, or talking through the node to someone else, circuit.
What about putting out a general call, like anyone want to chat?
Some node types, like Nitrum and the net, had a CQ command. You could type CQ followed by a short message, maybe 77 characters max.
And
The node would broadcast that message periodically in unproto mode, unconnected for others using the node to see. It would stay active for maybe 15 minutes. Others could see your CQ message listed under the user's command and connect directly to you. The node would translate your SSID for the CQ too, again using that 15N formula.
neat. Any other specific node tricks?
Well, the GAPPQ nodes often had a ports S or P command to list the different radio frequencies or ports they operated on. You could sometimes specify which port to use when connecting. And many nodes had a BBS command as a shortcut to connect to an associated packet bulletin board system.
BBS. Okay, perfect transition. This node network sounds like an information highway, and the BBSs were the destinations. Let's dive into those. What exactly was a packet BBS?
Think of it like an early online forum or community message board, but running on amateur radio. It was a central digital hub where hams could leave messages for each other, read public bulletins, and sometimes share files.
Like the old dial-up BBSs, some might remember?
Very similar concept, yeah. Just access via packet radio instead of a phone line.
So how did you get started with one?
No.
Connecting.
You connected just like any other packet station using the BBS's call sign and maybe an SSID. CW6PW2, for instance.
Then the first time.
First time connecting, you'd usually get a welcome message. It might ask for your name, your QTH location, maybe your zip code, and importantly, your home BBS. This info went into their user file.
Home BBS. Why was that important?
We'll get back to that, Sari. It was crucial for message forwarding across the network. After the initial setup, whenever you connected, you'd usually see a prompt. That meant the BBS was ready for your command. And like the TNC, if you were ever unsure, typing dot or H usually brought up a help menu.
Okay, connected at the prompt.
Yeah.
Job one is probably checking messages, right?
Absolutely. Managing messages was the core function. The commands were usually pretty intuitive, often just 1 or 2 letters.
Like,
R for read. RN would read new messages you hadn't seen before, Or R followed by a specific message number like R24112 would read just that message.
And getting rid of messages you'd read. Keep things tidy.
Yep, important housekeeping. K for kill. KM would kill mine, meaning all personal messages addressed to you that you'd already read. Or K followed by a number, K24112, killed that specific message. Kept the BBS from getting cluttered with old mail.
Makes sense. What about just listing messages without reading them all?
Lots of options there, too. L usually listed all new messages, bulletins, traffic, personal mail since your last visit. LL, followed by a number, like LL30, listed the last 30 messages total. Good for catching up if you hadn't logged in for a while.
Could you filter the list?
Definitely. LM listed only messages addressed to you. L followed by a call sign listed messages to that specific call sign or category, like LSALE. L followed by a call sign listed messages from that call sign. And L at filtered by the forwarding address.
So pretty powerful search tools, really.
Very much so. And if you wanted to see the full journey a message took, the forwarding path and timestamps, you could use RH, read header, or sometimes V view with the message number.
What did a typical message listing look like? What info was shown?
It was quite structured, you'd see. The message number assigned sequentially by the BBS. The status indicating type, B for bulletin, P for personal, T for traffic NTS and state, N for not read, Y for read, F for forwarded, etc. Important note, personal messages were only listed for the sender and recipient, but anyone monitoring the frequency could potentially see the content as it was transmitted.
Not encrypted then.
Generally not, no. Then you see the size and characters, the TO field, call sign, category, zip code, the from field, originator's call sign, and the at BBS field, which was key for forwarding.
Right, the address for other systems.
Exactly. Then the date time it arrived or was posted, and critically, the subject or title.
Why was the subject so critical?
Especially for bulletins, the subject, max 30 characters usually, had to grab attention and accurately describe the content. Something like FCC exams, margin, or CW really needed. A vague subject meant people might just skip it. For NTS traffic messages, the subject had a specific format, city, state, area code prefix.
And then the message body itself.
Right, the actual text. Recommendation was to hit enter around 70-75 characters per line to ensure it formatted OK on different screens. NTS messages needed the formal ARL format. To finish writing, you typically type Ctrl-Z or EX on a new line, hit enter, and wait for the prompt to confirm it was saved. Good practice to sign off with your name, call, and maybe your packet address.
Okay, that's reading and managing. How about sending a message?
Simple. S command plus the type. SP to send personal, SP to send bulletin, ST to send traffic NTS. The BBS would then prompt you for the address, the subject, etc.
And that addressing, especially for sending to someone on a different BBS far away, how did that at BBS part work?
That used hierarchical addressing. It was pretty sophisticated. The format looks something like addressee call at BBS call local-ya.state-province.country.continent.
Whoa, okay. Break that down.
So WB9LOZ at W6PW, #NCA.ca, USA.NOA. Send this to WB9LOZ. Their home BBS is W6PW. W6PW is in the #NCA Northern California local area, which is in CA California, which is in USA, which is in OA North America.
So it's like a nested geographical address for the BBS system.
Exactly, an area inside an area scheme. It wasn't a path telling it which hops to take, but rather the final destination's location within the global BBS network hierarchy. And critically, only one BBS call sign per address. Trying to put multiple addresses would confuse the forwarding and create loops.
Got it. And for bulletins or NTS traffic?
Bulletins were addressed to a category like SB Indifo or SV Sale at CA to limit distribution to California. NTS messages use the zip code and a special NTS designator, ST03431 at NTSNH. Send traffic for zip 03431 via the New Hampshire NTS gateway.
Beyond messages, BBSs often had file libraries, right?
They did. Usually a W command for what would list the available file directories or topics. WA might list files in directory A, or WARL might list ARL-related files.
And downloading or uploading?
D for download, followed by the directory and file name, like DFFCCE's m.lst. U for upload, again with directory and file name to send a file to the BBS.
Okay. Any other really essential BBS commands?
Absolutely crucial. B for BYE. Always Always use this to disconnect from a BBS.
Why not just use the TNC disconnect command?
Because BYE told the BBS you were leaving cleanly. It updated your user file, marked the time of your visit, reset your new message pointers correctly for next time.
Yeah.
Just disconnecting your TNC could leave your session hanging on the BBS side and mess up message tracking.
Ah, good tip. What else?
A for abort was useful if the BBS started sending a long lift or file you didn't want. It would stop the transmission. I for INFO usually gave details about the BBS itself. An I, or sometimes Q, followed by a call sign that accessed the white pages.
So white page is like a phone book for packet users.
Exactly. A distributed global database of packet users. You could query it with I call sign to find someone's name, QTHA, and importantly, their registered home BBS.
The one they entered when they first logged in?
Right. You could also search by zip code, IZZip, or location, IH city state. This White Pages database was updated automatically through the message forwarding network. It was incredibly useful for finding people and ensuring your messages were addressed correctly.
And that links back to the home BBS importance.
Yes. Because the White Pages linked your call sign to one specific home BBS, it was critical that you only registered one BBS as your home NH home BBSCAL command. If you told multiple BBSs they were your home, your mail could get stuck in forwarding loops trying to reach you at different places. Choose one.
Wow, a really sophisticated system built on relatively simple tech. Okay, so we've covered getting started, nodes, BBSs. What about really fine-tuning your own station, those TNC commands for customization?
Right. Beyond the basic connect, disconnect, monitor commands, TNCs offered a lot of ways to tweak performance and behavior. It gave operators really granular control.
Like what sort of things?
Well, things like 8-bit conv and all-in dealt with how the TNC handled 8-bit data, like binary files or executables, versus standard 7-bit ASCII text. You needed matching settings on both ends to transfer files properly.
Okay, for file transfers, what about optimizing for conditions?
AX25L2V2 was a big one. It let you switch between versions of the AX.25 protocol. Version 2.0 on-N was generally better for busy VHF-UHF frequencies. It sent short little pull frames to check if the other station was ready and had received the last packet, which reduced channel congestion compared to just resending the whole packet if an ACK wasn't heard.
But maybe not ideal everywhere.
Right. Version 1.0 OFF was often preferred on HF, where those little pull frames can just add to the noise so you'd tailor it.
Could you automate things from your TNC?
Yes, the beacon command, you could set it to transmit a short message automatically, either every n minutes or after n amount of inactivity. N was usually in 10-second units, so every 180 was every 30 minutes.
What would you beacon?
Useful stuff, hopefully, like mail waiting for WB9 LOZ or a club meeting reminder, maybe a severe weather warning. You set the beacon text and the path it should use, like unpiroto CQ. But you had to be careful not to overuse it and clutter the frequency.
Good point. What about handling flaky connections?
Chichiki N was important. It set a timer, and 10 seconds, maybe 30 for 5 minutes, for the TNC to automatically try and recover a stalled connection, or just disconnect if it seemed lost. Yeah. Especially useful with that AX.25 version 2 setting.
Could you leave automated responses?
Yeah, CMSG, connect message, or CTXT. You could store a message up to maybe 120 characters that your TNC would automatically send to anyone who connected to you. Useful if you stepped away from the radio. AFK, monitoring will be back soon, that sort of thing.
What's KISS mode? Sounds friendly.
Huh. Stands for Keep It Simple, Stupid. Turning KISS on essentially turned the TNC into a very basic modem, stripping away most of its own intelligence. This allowed more advanced software running on the host computer to handle the packet protocol directly. Things like TCP/IP applications often used KISS mode.
Ah, letting the computer do the heavy lifting.
Exactly. Then there were parameters like max frame. This set how many packets your TNC could send before it had to wait for an acknowledgement, usually 1 to 7.
Why adjust that?
On a really good, clear channel, you could set it higher, like 4 or 7, for a better throughput. But on a noisy or lossy channel, especially HF, setting it low, maybe even max frame 1, wait for ACK after every packet, improved reliability even if it slowed things down.
Tailoring to conditions again.
Always. M-filter was handy for monitoring it, let you filter out annoying ASCII control characters that some stations might send, like Control G, which would ring your computer's bell, or Control S, which could accidentally pause your screen scrolling.
Useful. Anything for seeing who's around.
M-heard, monitor heard. We kept a list of stations the TNC had recently heard directly or via digipeaters, often marked with an asterisk. Great way to see who's active on the frequency.
What if you wanted to see everything, even corrupted packets?
Pass all on. This told the TNC to display packets even if their checksum failed, meaning they were probably corrupted. Normally off-F, but useful for touching really marginal paths, just to see if anything was getting through, even garbage.
And managing collisions on busy channels.
Right, important stuff.
Yeah.
Persist and slot time work together. They implemented a system called CSMA Carrier Sense. Multiple access, basically, listen before transmitting, and if the channel's busy, wait a random amount of time before trying again. Persist controlled the probability of transmitting immediately if the channel was clear. Slot time defined the waiting interval. Setting these properly, like persist 60, slot time 10, really helped reduce collisions. You'd usually set another timer to wait to 0 when using these.
Sounds like optimizing Wi-Fi traffic today.
Very similar principles. Trans-S, transparent mode, was another way to send raw 8-bit data, bypassing TNC interpretation, but the receiver also had to be in transparent mode, and you couldn't use nodes or digipeaters. And TXT-LAY-N set a small delay after the TNC keyed the radio, but before it sent data, giving the transmitter time to stabilize, or the receiver at the other end time to recover.
Okay, so lots of knobs to turn. And for monitoring, you mentioned monitor on before.
Yeah, and usually related commands like mol on, monitor all packets, not just connected ones, msim on, monitor command converse most status, mrpt on, monitor digipeated packets, header and on, show packet headers, mstamp on, timestamp monitored packets needed D-time set correctly. Turning all those on gave you the fullest picture of activity on the channel.
Okay, let's unpack this a bit. It's amazing how much control these commands gave you, right? Real insight into the whole digital communication process.
Absolutely. It wasn't just a black box you plugged in. You could really get under the hood and optimize things for your specific situation, frequency, and conditions.
So, with all that technical power, what were the best practices? The tips for really making packet work well, maximizing performance, and what was the real-world impact?
Well, the absolute #1 rule for maximizing throughput, the actual usable information getting through, was minimize hops.
Fewer digipeaters or nodes?
Always. Use the absolute minimum necessary. Each hop just adds delay, increases the chance of interference or collisions, and drastically reduces your effective data rate. Direct connection, if possible, was always best.
Simple but crucial. What else?
Choose your frequency wisely. A less crowded frequency makes a huge difference. Just one extra station actively transmitting could potentially cut the channel's total throughput in half because of the shared nature and collision avoidance.
And the environment itself mattered, right? Especially VHF.
Hugely. Packet, especially at VHF UHF speeds like 1200 baud, was quite sensitive to noise and single path changes. A little bit of flutter or fading that you might not even notice on voice could break a packet connection. Long node paths were particularly vulnerable.
But conditions could also help. You mentioned fog.
Yeah, strange atmospheric conditions could have big effects. Thermal inversions could dramatically increase range sometimes. And yeah, operators in the San Francisco Bay Area reported that the dense summer fog often acted like a giant radio reflector, boosting signal strengths significantly.
Weird. What about signal distortion?
Multipath. Signals bouncing off buildings, hills, airplanes could arrive at the receiver slightly out of phase. Even with a strong signal, if the distortion was bad enough, the packet's error check would fail, leading to constant retries and terrible throughput. Sometimes moving your antenna just a few feet could fix it.
So if conditions were bad, what TNC settings helped?
You'd want to make the packets easier to get through. That usually meant decreasing packlen the number of characters per packet. Shorter packets have a better chance of sneaking through noise bursts. And decreasing MAC frame the number of packets sent before needing an ACK, maybe down to 1.
Smaller chunks, confirmed more often.
Exactly. Especially important on HF packet, which was typically run at a slower 300 baud rate due to the noisy fading conditions. There, you definitely use a short packlen, maybe around 40 characters, and a max frame 1.
Okay, smart operating practices. Now, beyond personal chats and experimenting, you mentioned public service, the National Traffic System, NTS.
Right. NTS is the ARRO's long-standing message handling network. It's all about reliably passing messages third-party traffic across the country, especially for public service and emergencies, a tradition going back decades.
And packet radio became a big part of that?
Increasingly so, yes. It became a vital tool for originating messages, typing them up and sending them into the system via a BDS, relaying messages between different points, and even delivering messages at the destination end.
Especially in emergencies.
Absolutely. NTS provides a trained network ready to handle large volumes of traffic when normal communications fail. The prime example everyone points to is the 1989 Loma Prieta earthquake in the Bay Area.
What happened then?
Communications were heavily disrupted, but the packet radio BBS network in the area handled over 7,000 NPS messages, health and welfare traffic, logistical messages for emergency services. It was a lifeline. Participating in NTS regularly built those critical skills needed when disaster struck.
So operators knew how to use the BBS commands for NTS traffic.
Yes, they knew how to find incoming traffic, LT command on the BBS, rid it, our MSG tag chaser, kill it once delivered, KMSG tag, and importantly, how to send outgoing traffic correctly using the ST zip code at NTSXX format. It was practical public service in action.
That really highlights the value. Okay, looking beyond those core uses, what was next? What was the evolving world of packet looking like as this source material was written?
Well, even then, there was more going on than just basic QSOs and BBSs. The introductory material didn't cover everything.
Like what?
Specialized networks were popping up. Packet cluster, for example, was huge for DXers hams trying to contact rare distant stations. It was networked specifically for sharing DX spots in real time.
A spotting network.
Exactly. An APRS automatic packet reporting system was gaining traction. That was all about transmitting location data, status updates, weather info automatically. Think early vehicle tracking and putting stations on a digital map. Very popular for events and mobile operation, especially once GPS became integrated.
And connecting packet to the wider world.
Yeah, that was happening too. Programs like JNUS and TNUS allowed running TCP/IP over packet radio.
TCP/IP. So connecting packet networks to the actual internet.
Essentially, yes.
Yeah.
Bridging those two worlds. There were other networking protocols too, like TextNet and ROSE, and even amateur satellites carrying packet radio payloads.
Yep.
The PacketSat-E program.
Wow. And speed improvements.
Definitely on the horizon. The source mentions high-speed modems, pushing speeds up towards 56 kilobaud, were just around the corner for amateur use. A big jump from the common 1200 or even 9600 baud.
So the field was clearly still moving fast. How did people keep up, stay current?
Good question. Joining a local packet radio group or a digital communications club was probably the best way, sharing knowledge, troubleshooting together.
And national organizations.
TAPR, the Tucson Amateur Packet Radio Corporation, remains central. Joining TAPR got you newsletters, access to kits, software, and kept you plugged into the core development community.
What about magazines?
Oh yeah. Reading the packet columns of the big ham magazines, QST, CQ73 magazine was essential. And just checking the local packet BBSs regularly for bulletins about new software, hardware mods, system changes, that was crucial too. The landscape was definitely dynamic. Digital communications, including packet, was clearly still evolving.
Which brings us nicely to the end of this deep dive. We've really journeyed through packet radio, haven't we? From those surprising Canadian origins.
Right, and the development of the TNC.
Through the power of node networks and digging deep into how those packet bulletin board systems worked as information hubs and public service tools.
Yeah, the key things to take away, I think, are the ingenuity of that error-checked communication over radio.
Definitely.
The huge efficiency gain moving from simple digitpeaters to intelligent node networks. And just how much hidden depth there was in those BBS systems for sharing info and coordinating efforts, especially when it really counted.
So as a final thought to leave everyone with, just consider how this old technology really laid down some foundational concepts we just take for granted now in our always-on digital world.
Things like network routing, robust error correction, even decentralized information sharing. Packet radio was doing versions of that decades ago.
So maybe the provocative thought is, what principles of reliably exchanging information are truly timeless? Which ideas transcend the specific wires or radio waves we happen to be using at the moment?
That's a good one. We definitely encourage you, if this sparked your interest, to look into modern packet activities that's still out there. Or just take a moment to appreciate the cleverness behind these pioneering digital networks.